Good morning, November 24th, and we've come to problem 9, and they start defining some concepts. So I'll start by making an example and see if I can understand this. So it's generalization of Gauss sums, and they'll use it later. Excellent. A ring of integers in a number field. So I'd like to have two examples, and the one is of course the rational integers, and then as the other one, I thought we could let k be the rational numbers extended by square root 2, and the integers of this field is just set extended with square root 2. So we take the first example first. I think that should be easy. Now we have a non-zero ideal . So that be the table of multiply of 6. An additive character which is non-trivial on any additive subgroup of the form my God. So we have the ideal, then we need to see what are the strictly larger ideals, and that's why I chose 6, because we have 2. It is non-trivial on these guys. That's a little weird. This must map to unity. Yes, to unity, of course. And then I'll just color them in another color. That means that 3 mustn't map to naught, or to unity, neither must both 2 and 4. So if this maps to omega, then this maps to omega squared, and this to unity. So that's, what is it called? That's trivial, because on the blue ideal, J2, it's trivial. Of course, we can map it into itself, and then the usual map into the 6 points on the unit circle of So if this maps to, say, omega didn't work, so omega bar doesn't work, so let's try the last possibility. Minus omega squared. 1 plus 1 gives 2. So we multiply by, we square it, it's omega. And it's minus 1. And then this must be minus, no, I'm not sure. It's plus omega squared. And this is minus omega. So there are only two which are non-trivial. Now this becomes quite complicated. I'm not sure I want to do that example, but I better do it. If we just take the ideal generated by 2, which of course is square root of 2 squared. So let's just take the norm of the ideal. That's 6. Norm of J1 equals 2. By the definition here, we only have 2 elements in the residue ring. Or should we say it's the additive character? So it's just the additive group. And it's generated by the unity. Well, never mind. It's generated by 2, and of course the norm of J2 equals 3. Now this is 1 plus square root 2. So the ideal generated by 2 it equals the span of 2 and 2 square root 2. So it's in coordinates so the determinant of this is 4, so there should be 4 elements. naught, 1, 1 plus square root 2, and square root 2. And then they're just translated. Right. So an additive character here. So we can define 1 and square root 2 like we wish. Then this sum. Oh, and then they must be plus minus 1, of course. So let's check it. So it's the map of 1 and of square root 2. When they both map to unity, that's trivial. Now we have only one ideal, larger than R, and that's the ideal generated by square root 2. And I just need to read it once more. Which is non-trivial on the additive subgroup of the form J modular I for any larger ideal. Yeah. So we need to check the ideal of square root 2. Then these guys. So that means that it's only 0 and 1. So I believe this guy is non-trivial, whereas these two are trivial. On the other hand, oh yes, I don't like that 2 in the ideal maps to different, but that happened up here as well, that 2 and 4 lying in the ideal maps to different guys. All right. And then the multiplicative group. So up here, the multiplicative group consists of 1 and 5. So we've only got 2 there. However, we choose this guy, and that's any guy, and then it's defined to be naught anywhere else. And what have we got down here? The multiplicative group the point is that square root 2 when we square that, the product of it with the squared lies in the ideal, so it's not in the multiplicative group. So that's just unity. So that was too simple an example, a little too trivial. But then if I've said something like the ideal generated by 6 would have had 36 elements, and I couldn't write it here. But then how do we map square root 2 maps to naught, and then unity maps to 1, or 1 maps to unity, and then this guy is the sum. That's not relevant, it's the product of Can we choose that freely? So my question is it possible that 1 plus square root 2, it's a unit, of course, so that must actually be in the multiplicative group as well. Interesting. If we subtract square root 2 twice, we get 1 minus square root 2, and the product of them is minus 1, which is equivalent to 1. All right. So this must of course map to unity, and this may either map to plus or minus unity. Okay, now I have a feeling of what we're dealing with, so let's I'll just take a pause and then write the problem on the next page. So I've written the definition of G of chi, and then the guy we should work on. And actually here chi of x vanishes when we are not in the multiplicative group, so let's just make this the multiplicative group. And A, could that be any? I would like to define y equals ax. So we can only isolate x if A lies in the multiplicative group. That's what it does. It says here it lies in the multiplicative group. All right, then it's trivial, isn't it? We just substitute here. And take it outside. And we are on the unit circle, and oops, and this is just G of chi. So the great problem was understanding what we were dealing with, not solving the problem. So that was A. And next, to solve B, I need to read the next paragraph here. So I'll just take a break while reading that. And if you don't have it, you can pause here. I have had my break, been downtown buying coffee, and let's work a little on the next problem, or rather the next part. This definition of primitive multiplicative character we need to work on. And I think we should work on set modular 6 set, because when we have the ideal, then in the quotient ring, that has an interesting character with various ideals. So that are the members, and 6, let's work on 12 instead, because the other one is too primitive. So naught plus minus 1 plus minus 2 plus minus 3 plus minus 4 plus minus 5 and 6. Right. The ideals 12, there we have 6 and 3, or 4 and 2. Of course, the ideals generate by 2 and 3 being the maximal ideals. And we need to have a list of the characters. So let's find the multiplicative group. That's not needed. So that's very easy. This one and 6 lies in this ideal, and 3 and 6 in the other. So there's only plus minus 1 plus minus 5 left. And the square of each one is 5, unit element. So this is isomorphic to the Vienna group with 4 elements. So let's write up the possible characters. There's the trivial guy. And then minus 5 comes by multiplying 1 and 5, so it gives minus 1. That's not T2, it's chi2, that's chi1, chi2. There we go. So we have 4 characters, and each squared gives the trivial one, so that means that the character group is the Vienna group as well. All right. Now we have to find out which one was it primitive, they said? Primitive. So we take each ideal and take the elements in here. Take each ideal and take the element in here that lies in 1 plus it. So we'll just take 1 plus for each of them. This is actually more logic, isn't it? All right. This is contains the 4 elements of the multiplicative group. So these 3 are non-trivial. This one is 1, 5. So this one is not primitive. Of course, it's trivial on this group. And 7, that's minus 5. I have to take them out. This one is obviously primitive. And 1, 5, that was this guy. And 1, 7, that's this guy. And 1, 7. So we actually have one character that is primitive. That's a little weird because we use the additive structure as well. What I'm wondering about here is, does such a guy exist for all ideals or for all quotient rings? But in this case, one exists. And what does that mean? That means for all I would very much like to be able to prove that such a character exists. So we have to find a characterization of all the elements in the multiplicative group that comes from this. Minus 1 came as well. I need to reformulate this. But let's go to the problem and then see if I know enough to solve it as it is. If chi is primitive, show that this formula also holds if A is not a member of the multiplicative group. Therefore, we should look at the ideal generated by the A's, or generated by A. So the first claim is that A is an ideal. If it wasn't, then all of the ring would be generated as a multiplier of some element in R times A. And that means that A has an inverse, and therefore it's a member of the multiplicative group. So this is the first thing. Next step is then so that's what we know. And also 1 plus AB, of course, it's not naught. And X lies in the multiplicative group. So maybe we could use this element for A up here. When A fails to lie in the multiplicative group, this vanishes. So we really have to show that the sum vanishes. out of ideas, so time for a break. These are busy days. It's November 25. I have little time to work on problem 9. I wanted to make another example. I've never been working very much with Dirichlet characters. I know it's not pronounced Dirichlet in English usually, but he was German, so I think it should be pronounced the way it was pronounced in German in the 19th century. Or maybe not necessarily, but a little respect. So we work with set modular 12, the integers modular 12, the multiplicative group, and as the additive character we use the standard one. And on the multiplicative group, I can see there are 4 characters. So this is the Vienna group, and so is the group of characters. I wrote this up because we need to see which characters are primitive. And that means that on all these 4 sets, they need to be non-primitive. And of course, it's only the 2 smaller sets that are interesting. So one take 12 and then take 3 out or 2 out, that gives 6, and 3 out, that gives 4. And then we have the side classes that we need to test. So it's 1, 5 and 1, 7. So this one is trivial, so it's not primitive. This one is and this one is not primitive because it's trivial on 1, 5. This is trivial on 1, 7. So chi3 is the only trivial. And it's the only trivial. In preparation of 9C, let's just compute the Gauss sums of each of these guys. And to do that, we need the values of psi as well. We are black. I should have made space for that. Psi of x. There's no room for that. I'll do it up here. And let's take the unit circle. This, of course, is 1/2. That's 60 degrees plus square root 3/2 I. So that's cosine and sine of 60 degrees, 30 degrees. Oh, I'll write it as a number, complex number, not coordinates. And then 5. Yeah, it's just this one times the imaginary unit. And 7. Oh, that's the conjugate of this guy. this is as well. So I'll just write it up. Alright, we're ready to do the characters. The character of the trivial guy is the sum of them. And of course, we can disregard the imaginary parts. They add up to naught. So it's square root 3 minus 1. And the modular of this guy is 10. No. Is which is 4 minus 2 square root 3. Well, and g of chi1 equals so those two added and those two subtracted. Those two added minus those two. So that means the real numbers vanish. And that gives that gives I. So it's plus plus minus plus plus minus minus, right. Where on earth did I put that? It was chi3, which is trivial. So this is chi3. D of chi2. It's plus, minus, plus, minus. So that means they are added separately. Oops, there's a mistake here. 11 must be minus I halves. So those two added and those two added. That means those two subtracted and those two subtracted. So it's that one minus that one giving I, and that one minus that one giving minus square root 3I. And finally, g of chi3, the sum of these two, square root 3 halves, no, square root 3, minus the sum of 5 and 7, that gives minus 1, that's plus 1. these two added square root 3, these two added minus 1, and then subtracted plus 1. And the norm of this should be the square root of 12, or the modular of this should be square root 12, which is 2 square root 3. That's not what I get. You can pause the video and find the mistake. I'll just pause the recording and then try to find the mistake. All right, 1 minute passed. The mistake was that I used the wrong root here. The root I should use must be minus this one here and minus this one here. As I've written, it's plus minus 5, so plus minus 1 and plus minus 5. That doesn't make any sense. But 5, that lies over here. That's the reflected in the imaginary axis. So I'll just correct the mistakes and then make a cup of coffee and then start on the next. And that's an explicit calculation of the sum we need to work on. I'm back. I've corrected the error now. So these are the new points. And then the sum of all these points, which are symmetric around naught, vanishes. And so do these, by the way, because these are opposite. So the sum of these two vanish. Now what was that? Here, the sum of these two vanishes and the sum of the other two vanishes. So that's naught as well. And this one gives 2 square root 3 as it should be, because we add these two to square root 3 and these two to minus square root 3 and then subtract them from this. That was the first thing to compute the g values. Then we should compute the sum chi of x times psi of ax for some a, and let's just take 2. And see what we get. So I would like to see why that vanishes. So this was psi of x. Now we need psi of 2x. So this is the right guy. And 10 this is 6, 9, 10. This is 11, so this is 10. If we add them, it gets 12, so it's just the conjugate. And 14. By God, that's the same. It's kind of obvious, by the way, isn't it? I mean, the same as 1 maps to. not the same as above. And 11, that gives 22, that's the same as this guy. Now what should we call that? G2 of chi. So G2 of the trivial guy. That's just the sum of these. 1, 1, 1, 1, 1, 1, 1. This is very weird. That's interesting. These cancel, of course, so it gives 1 plus 1, that's 2. In chi 1, we add these two, giving unity, and these two giving unity, and subtract, they vanish. Chi 2, then we add these two and subtract the sum of these two, so that's square root 3i minus square root 3i. And by the book, this guy should vanish. So we add these two, giving 1, and subtract the sum of these two, right, it vanishes. Should we try with G3? I don't think there'll be much insight obtained from that. Of course they map. Here the points mapped 2 to 1. Here we're using 3x, 3 times, we'll get the imaginary unit here, and minus 1 and minus I, and I don't know. Let's just do it. So 3, that gives and 5, that's 15. That's I as well. 7, that's of course conjugate, and 11 as well. All right. G3 of the trivial guy is naught. G3 of chi 1. That's I plus I plus I. Here we add these two naught and these two naught. We add these two naught and these two naught. That gives naught as well as it should. So now I've made my examples, and I had a suspicion that they wouldn't give me any insight in the mechanisms at play here. It is now 20 minutes past 4, and it's becoming dark now, so I turned on some light. Well, I did get an idea after my coffee break, looking at this once more. I got this idea that, say, chi is non-trivial on this group. That is, I don't know what that is in English, to take the common set and the multiplicative group, or rather those of these that lie in the multiplicative group. If chi is trivial on 1,5, that is, which happens for the trivial ones and for chi 2, then the sum in question vanishes. And the idea was that when we multiply by 2, then we have a collapse of values. And when we multiply by 3, we also have a collapse of values, in both cases 2 to 1. If we multiply by 6, they all map to -1. So we have 4 to 1 collapse. So definitely the sum shall vanish for all of these guys, except the trivial. Oh, for that one. I'm not really sure. 6. That's 1 and 7. So that means that it will vanish for this guy, the trivial one, and for this guy. I'm not sure about this. So that's the idea. Hi again. Back on Monday, November 28th. Time to work a little more on this problem. I have been doing a little homework during the weekend, which I'll tell you about in a moment. But first, this formulation seemed to be a little wrong. It seems that these two values that I called A, both of them should be somewhat dual in relation to 12, such as A is 3, then it should be 2 or 4 here. And when it's 4, then it should be 3 here. So I didn't get this quite right. When working on it, I thought a little about some basics I'd like to get straight. Now that we're working in a general setting, I would like to prove things in more generality, not just having a good intuition about them, but we'll return to it and see what we actually need. The essential way to start is to ask yourself, I think now, what is the condition that psi of two distinct x values give the same, and then we can set that outside parenthesis. So that's the idea. And since they occur in the sum, we need only to use values of x in the multiplicative group. So this is an additive character. Yeah, we can put that outside a parenthesis straight away. And now we need to know for which values this happens. And actually also A should not lie in the multiplicative group. We should call that something. Let's call it capital M. Just to make sure, cannot be misunderstood. And then we need to, now A is in a ring, so we actually have a one element. So we can see where that maps. Have we used n for anything? No. And of course, k and n may have no common denominator. It's called common divisor. So that means a times x minus x1 minus x2 must be a multiplum when we put that up here. Now what am I actually doing here? When we put that in psi here, then we get this value, and so it's e to 2 pi I k divided by n. That must give unity, and that means that it's a multiply of 2 pi. So that means that n divides ka x2 minus x. N and k have no common divisors, so that can best be disregarded. And then we use the trick dividing by the common divisor of n and a. I'm really glad that I discovered that trick. And that means that n divided by n minus a must divide the difference between the two x values. And that means that x2 must be x1 or x1 plus n divided by etc. up to I don't know how much. Well, that must be the common divisor. Oops. The common divisor minus 1 times n. Yeah. I'll just do it like this. And that times, it's 1 times and x1 times 1 plus this, and x1 times 1 plus this, etc. So that means that we should look at the set and now you can see why we get I don't see it anywhere here. That you say 1 plus the ideal. So it's the non-trivial additive group. I didn't quite. I thought it said 1 plus somewhere here in the definition. I'll just take a break and find it. Found it. It's here, congruent to 1 modulo j. So that's the groups we're interested in. So it's 1. Yeah, and this we could actually generalize. 1 plus I that's not necessary. And we only need those that lie in the multiplicative group. So we'll take the intersection, the cross-section with that. Of course, this may only contain one element. And then there will be no primitive character. That was another question I had. Are there always a primitive character? We'll just write that down. And now, which is the setting? It's a general ring, so the problem will probably be negative. I claim that S is a subgroup of M. It consists of the elements of M that can be written in this form. And when we multiply them, then we get one of the same kind. We need to find out that the inverse of an element of this form will lie in the group as well. Let's leave that for the moment. No, I can't stop thinking about that. So I'll just look into it. Does the inverse of a guy in here also line S? Well, assume that we have a guy and multiply it, and it gives unity. That means that x, or maybe we should write it like 1 plus x and then conclude that it like, I think we should do that. So that's 1 minus x plus in divided by n. And it's a normal equation. We do the usual stuff. It actually gives unity, of course. I had already deleted them in my head. So, is this guy x a number times n divided by na? It doesn't seem so. Interesting. I'll have to look at that and then I'll be back. All right. I think instead of a subgroup, we should rather realize that we're dealing with a ring, not a group, and then define the ideal generated by, where was it, this element. And the difference of two values shall be in this ideal for them to give the same, for psi of them to give the same. And that means that it's a good idea to look at that we can't call it I, we must call it J. J. So we look at the side classes. And we choose a set of representatives there. And let one of them be unity. So we have x naught equals naught, x1 equals unity. And of course still we have A does not line the multiplicative group. So this is So this is not 1. They are distinct. And then we carry on choosing representatives up to xm. So there are, we assume, m side classes. And then we should split up. First summing over side classes. And then summing over elements. That's a little complicated. Chi of x, psi of ax, and x, I should write it down here, but I think it's better to write it here, lies in, what do we call, the ideal is called dA. So x lies in x, y plus dA, and in the multiplicative group. And the point is, for all these guys, psi will have the same value when they have the same representative here. So this guy can be put outside. And now I would like to reduce this to the case summing over x1 equals 1. So can we put x? We can put xi outside because that has an inverse. And now I would like that this sum vanishes. So that was actually where I needed that this was this formed a subgroup of the multiplicative group. In that case, I would be able to prove that the sum vanishes. So that was what I wrote up here. So let G, now we write it additively, be a finite commutative group. The image has this form for some n. So let's choose an element of the group where n has the largest possible, where the denominator is the largest possible. And then the usual trick, let's call them something else. So we have I and j's, so this gives unity. And then we take psi of the jth power of g. Now that's very weird. 2pi ik, that's 1 minus jn. The n's cancel in the last expression, so this gives unity. So that means that 1 divided by n occurs. So this is a guy that maps to the first element on the circle of that kind when the circle is split into n points. And that means that for some we will actually need the structure theorem here. But now let's just take the sum over all the powers of that g. You see, if we use the so we had to use the structure theorem. We do this for each of these cyclic groups. So let's say we've done it here for this guy, and then we have to do it for the others as well. That actually doesn't matter, because it's sufficient that the sum over these vanish. So I'll let this be the largest, the subgroup of the largest order, and then sum over those. If it's trivial, we'll of course get the cardinality of G, and if it's not, then it's the sum of values of this. For some k, 1, 2, and then it's a multiplum of n, some multiplum of n, say z times n. And this is a power series if it's not unity. So we just use the formula for the power series. You know what, we sum from 0 to -1. That's easier. Then it's I to 2pi zn divided by n minus 1 divided by There's this difference, but the numerator will vanish. So that was not very well done. So it's naught divided by something, and that gives naught. That was my idea here. So you see, I have been working on it, but not quite been able to solve it. So there's still a tiny little bit missing. Time for a break. Well, time flies. 4:30. I realized that I had to complete what I started doing, proving that 1 plus this ideal, the intersection with the multiplicative group, actually is a group. Let's take an element in there. And then the inverse, it lies in the multiplicative group. And the inverse will then be in some side class, say y plus zb, and then we multiply the two guys. This should have been a b is okay. We have b as a common factor. Xy plus z plus xzb times b. And that means that this guy, that's a multiple of b. So this can only happen if y minus 1 is divisible by b. And that means exactly that yeah, what does that mean? It means that it's some element. How far are we? V times b. So that means y equals 1 plus vp. So it lies in 1 plus the ideal. So it has the form to line G. So that I believe that this finally proves B. So I believe C is very much like what we have been doing already. So we have the sum, let's do it, E of chi, E of chi bar, chi of x, psi of x, chi bar of y, psi of y, psi of chi of x divided by y times psi of x plus y, and we introduce the new variables. And as far as I remember, or maybe we have some new stuff going on here. Of course, we have x point y lying in the multiplicative group. This is actually slightly different than what we have done before, isn't it? If they have opposite sign, then they map to -1. So we have x plus y naught, then u equals minus unity. And otherwise it's 1 to 1. But I forget how we do it. We have to solve for x and y, so we multiply this by y. Now what's the point of that? Yeah, and just insert it in there. X equals uy. And now in general, u plus 1 need not at all be invertible, even if because it's not the only exception. So we need to find out what happens when we let x and y run through the multiplicative group. Which values can we actually get? Oh, that's interesting. It's confusing. I don't know what to do. So that's it for today. Good morning, November the 30th. I think I finally knacked part C. This was my first attempt. You see, the idea I tried various stuff that didn't work, but now I've got another idea, and that's to use part B. So we take this part first, and instead of y, we call it A, chi of A, psi of A, and then g of chi point psi. Never mind, let's just write the sum. And then we use the result of problem. Oh, I just made a mistake. It must be the conjugate. And then we use part B, that this means we can sum over a times x instead. And the two psi's, they are additive. Chi of x, psi of a times 1 plus x. And we can take out the summation of a here. So we just take a sum chi of x and then summation over a psi a times 1 plus x. And in the last sum, I was previously only adding over the elements of the multiplicative group, and then it's difficult to see what this will make. But up here we can change the sum to be over all of the entire ring. And if we do that, then this is yes, what is it? It's not quite clear though, but rather clear that if this is distinct from naught, then it will give naught, so the sum will vanish. So it's only when x equals minus 1 that we get a positive result. So it's only chi of minus 1 times, and then the sum of unity, which of course is the number of the cardinality of our finite ring, and which is equal to the norm of the ideal. It's interesting how difficult it was for me to find this. I have worked intermittently during some days, and I must say that doing this simple thing never occurred to me. Just doing this never occurred to me. And that's of course because I already knew we had solved it once doing this. And when I did this, I wasn't aware of this formula, that this might be written like this. That's part B of the problem. So I was stuck in the old way of doing things. All right. So that's the first part of section 2. The next we shall try to prove complicated theorem. See if that takes me all of December.